Imagine cruising at flight level 350, the autopilot suddenly drops offline, a continuous stall warning blares, and the digital safety net you've relied on for your entire career just vanishes.
Right. You've got a handful of seconds to diagnose the aircraft's energy state before you cross the edge of the aerodynamic envelope.
Exactly. We are conducting a closed-door technical debrief today for you, the senior line captains, regarding A320 upset prevention and recovery training, or UPRT.
Our mission in this deep dive is to dissect recent loss of control in-flight incident reports. We need to trace the flight control law degradation pathways.
And really figure out the exact ECAM logic that triggers severe automation surprise on the line.
We are pulling our data from engineering reports, high-altitude aerodynamics telemetry, and specific case studies, notably AirAsia Flight 8501 and XL Airways Flight 888T.
Since you are operating on the line, you already know the baseline systems, so we're skipping the basic definitions today. We're drilling directly into the why and how of system reversions when the digital protections fail.
To understand how the systems fail, we first have to establish the physical reality of the environment where these anomalies manifest. Up at cruise altitudes, you're operating within highly restrictive aerodynamic margins.
Right, we are looking at the boundaries of the coffin corner.
Exactly. For our fly-by-wire aircraft, the low speed margin, which is indicated by VLS on the speed tape, is calculated as 1.23 times VS1G.
And as you climb, that low-speed margin is actively converging with your high-speed structural or Mach limits, indicated as VMO or MMO.
Because the physics of high-altitude operations dictate that convergence. The lower air density up there requires you to fly at a significantly higher angle of attack simply to generate enough lift to maintain level flight.
So your baseline angle of attack is already elevated, which means your margin to critical airflow separation is drastically reduced.
Right. Consequently, low-speed buffet onsets at a much higher true airspeed than it ever would in dense low-altitude air.
And this aerodynamic reality forces a critical differentiation between buffet types on the line, doesn't it?
It does. High-speed Mach buffet, which is caused by unsteady shock waves developing on the upper surfaces of the wings as you approach the critical Mach number, manifests as slight vibrations.
Though modern Airbus fly-by-wire aircraft rarely experience severe high-speed buffet, even near design limit speeds.
Correct. Conversely, a low-speed stall buffet occurs when the airflow physically separates from the wing.
Yeah.
This is a violent, heavy deterrent buffet.
I mean, the pressure distribution is constantly changing, generating heavy structural vibrations designed to compel an immediate manual response.
But this brings up an operational contradiction in the incident reports.
Right. If a high-altitude deterrent buffet is genuinely that violent and airframe shaking, why are we seeing line crews misdiagnose a Mach buffet for a low-speed stall buffet?
Well, assuming their basic instrument cross-check is standard, the difference should be obvious. But when you look at the flight data, you see that the moment the startle reflex hits during a sudden high-altitude upset, the standard instrument cross-check frequently degrades.
So pilots regress to relying on sensory feedback rather than immediate primary flight display speed trend verification.
Exactly. The critical verification step isn't just feeling the vibration in the airframe. It is explicitly checking the airspeed trend vector.
You have to ask, is it pointing toward the amber VLS line or the solid red V alpha max strip?
Right. If the trend is decaying into those parameters, the vibration is definitively a low-speed stall threat.
But if the trend indicates acceleration toward the lower end of the red and black strip, marking the Mach limits, then the vibration is high-speed shockwave separation.
So, establishing those narrow aerodynamic margins brings us to the system degradation logic itself. When sensor anomalies occur in the coffin corner, the aircraft systematically strips away its own protections.
Let's trace that degradation from normal law to alternate law. We typically see this triggered by multiple failures of redundant systems.
Like a dual air data reference disagree. When the system drops to alternate law, you lose the absolute high angle of attack protection.
And it's replaced by a conventional synthetic stall warning, plus basic low and high-speed stability.
Right. The stability logic will gently push the nose down if the speed drops too low. But crucially, you can override that with the sidestick.
Which brings us to the XL Airways Flight 888T accident. It provides a clinical demonstration of how vulnerable this degraded state can be.
Yeah, this was a post-maintenance test flight, and the aircraft was subjected to a low-speed handling check.
3 days prior, during a high-pressure wash, water had actually entered the first and second angle of attack vanes.
And during the flight, at altitude, that water froze. Both primary sensors mechanically locked in a static position of approximately 4 degrees.
Which means the flight computers did not detect a failure, because the sensors were reporting a valid, steady 4-degree measurement.
The system simply sees a steady state. So as the crew reduced thrust to idle and the airspeed decayed, the actual angle of attack increased rapidly.
But the system remained totally blind to the changing aerodynamic state. That explains why the alpha floor thrust and the high angle of attack protections completely fail to activate.
Correct. The system logic inherently relies on accurate AOA data to trigger those protections. That mechanical failure led directly into a critical logic trap.
You're talking about the alternate to direct law reversion.
Right. As the airspeed decayed below 100 knots, the crew extended the landing gear. Because the autopilot was already disengaged and the system was operating in alternate law, the simple act of extending the gear
Automatically triggered a downgrade into direct law. Wait, let's visualize the pitch trim trap that materializes at this exact moment, because this is where the system logic turns lethal.
Let's break it down. During the initial deceleration in alternate law, the low-speed stability was trying to lower the nose.
But the pilot was pulling back to maintain altitude. So the auto trim actively wound the trimmable horizontal stabilizer, the THS, to its full nose-up limit of 18.6 degrees.
Right. And when they dropped the gear and transitioned to direct law, the auto trim instantly stopped. It displayed the amber use a man pitch trim message on the ECAM.
Think of that THS stuck at 18.6 degrees nose-up as a fully loaded physical spring. The moment the crew recognized the stall and applied Togier thrust, the massive nose-up pitching moment of the underwing engines acted as the release of that spring.
That is the exact aerodynamic reality. The combined upward force completely overrode the elevator's forward authority.
The underwing thrust couple, combined with an 18.6-degree nose-up THS, physically exceeds the aerodynamic authority of full forward sidestick deflection.
You are in an unrecoverable aerodynamic stall at that point. This highlights the clinical importance of that use-man pitch trim ECAM message.
Because in direct law, you are flying an unprotected, conventionally trimmed aircraft.
Exactly. If you fail to manage the THS manually with the trim wheel, your thrust applications will dictate your pitch access regardless of what you do with the elevator.
This physical trap we are talking about directly feeds into the human response. Let's pivot and look at the telemetry from AirAsia Flight 8501.
We need to see how automation surprise completely breaks down the mental model in the cockpit. We move from a mechanical failure to the crew's psychological decoupling from the aircraft's actual mode status.
Right. In the AirAsia 8501 sequence, the aircraft experienced repeated master cautions during cruise. This was due to a cracked solder joint in the rudder travel limiter unit.
And after executing multiple ECAM-directed resets, the captain made the decision to physically pull the flight augmentation computer circuit breakers in flight.
Which is a drastic action. It immediately forced a reversion from normal law to alternate law. It disconnected the autopilot and the auto thrust.
And crucially, it initiated a 2-degree uncommanded rudder deflection, which induced a roll.
Because the FACs control the rudder travel limits and yaw damping. When you pull the breakers and they go offline, the rudder can deflect slightly.
Right. This is exactly where we observed the onset of the startle effect and severe mode confusion.
The first officer, who was the pilot flying, experienced immediate spatial disorientation in instrument meteorological conditions.
He reacted to the sudden roll in the autopilot disconnect by overcorrecting laterally, and then he applied continuous full-aft sidestick.
The situation was then severely compounded by a breakdown in crew resource management. The captain issued an ambiguous command. He said, "Pull down."
Think about the cognitive dissonance in that phrase for a pilot experiencing spatial disorientation. Pull reinforces the physical aft sidestick input,
while down indicates the intended flight path. It completely exacerbated the first officer's cognitive tunneling.
He maintained full aft stick, which resulted in a climb exceeding 10,000 feet per minute, driving the aircraft directly into a deep stall.
We also have to look at the extreme danger of the first officer's lateral overcontrol in this degraded state. When you are operating outside of normal law, fly-by-wire systems do not provide yaw envelope protections.
Right. If a startled pilot attempts to correct a sudden roll with rapid, alternating full-scale rudder inputs, which is a reaction noted in the American Airlines Flight 587 accident and the Air Canada wake turbulence encounter, they risk severe structural failure.
Cyclic rudder reversals can subject the vertical stabilizer to lateral loads exceeding 150% of their ultimate design limits. The rudder is simply not a primary roll control surface during an upset.
You must respect that aerodynamic limitation. You must never use the rudder to induce roll during a high-speed upset unless all primary lateral controls have completely failed.
But this brings up a pointed human factors question regarding the AirAsia data. How does a highly experienced line crew completely ignore a continuous blaring auditory stall warning while holding full aft stick all the way to the ocean surface?
I mean, we are talking about professional aviators here.
Right. It seems incomprehensible.
The behavioral data points directly to the out-of-the-loop syndrome. Line crews spend 99% of their operating hours in normal law, where the flight computers actively prevent an aerodynamic stall.
Over thousands of hours on the line, the belief that the aircraft simply cannot stall creates a profound cognitive block.
Exactly. When the startle reflex triggers, it completely overrides trained instrument scans. The pilots regress to their conditioned normal law habits.
So they fight the aircraft's degraded alternate law state with inappropriate inputs.
Because their mental model says the plane cannot stall, they interpret the sudden loss of altitude and the alarms not as an aerodynamic stall, but as an automation failure.
An automation failure that they feel they must muscle through by pulling back to maintain altitude.
With that human-machine interface breakdown diagnosed, let's step through the exact procedural execution required to recover from these degraded states.
Because executing the A320 technical recovery SOP is not intuitive when the startle reflex is active and alarms are blaring.
The A320 stall recovery memory items demand absolute precision. At the first indication of a stall, whether it is the oral warning, the deterrent buffet, or the visual PFD red alert, the pilot flying must announce, "Stall, I have control."
And you must immediately disconnect the autopilot and the auto thrust. Leaving them engaged while attempting a manual recovery will result in the autoflight system fighting your inputs.
Right. The system will create unexpected and hazardous trim or thrust adjustments while you are trying to fly the wing.
So priority one is unloading the wing. You must apply continuous nose-down pitch control to reduce the angle of attack until the stall indications cease.
Altitude loss is entirely secondary here. If you are focused on the altimeter unwinding, you will hesitate to push the nose down and you simply will not break the stall.
And if the aircraft is severely out of trim, as we analyzed in the XL Airways data with the THS spring effect, you must manually and aggressively wind the pitch trim wheel forward.
The sequencing of your roll control is equally critical. You must roll the wings level only after the angle of attack has been reduced.
Right, because if you make lateral sidestick inputs while the wing is still aerodynamically stalled, you are commanding the deployment of ailerons and spoilers on the retreating wing,
which changes the camber and destroys whatever marginal lift remains on that side, risking an immediate asymmetric stall or an unrecoverable spin. You must unload first, then roll level.
Now, regarding thrust management during the recovery, you must retract the speed brakes immediately to eliminate parasitic drag. Then apply thrust smoothly.
Do not slam the thrust levers to the TOGA detent. As we discussed, the A320 has underwing mounted engines. A rapid, maximum thrust application creates that massive nose-up pitching moment.
If you apply TOGA before you have sufficient airspeed for elevator authority, that pitching moment will pitch the aircraft right back into a secondary stall.
We need to strongly contrast this stall recovery procedure with high-altitude overspeed management because the inputs are fundamentally different.
If you encounter a severe overspeed due to a wind shift near the coffin corner, the rule is the exact opposite. Keep the autopilot and the auto thrust on in.
Right. The auto thrust will automatically command idle, and the autopilot is highly robust at maintaining the flight path safely without inducing extreme G-loads. You manage the overspeed by expending the speed brakes.
And if the overspeed is severe enough that the high-speed protection actually activates, it'll automatically pitch the nose up and disconnect the autopilot.
If that happens, you keep the speed brakes extended and make only smooth, conservative inputs. Snatching the sidestick backward at high Mach numbers will induce severe G-loads and high-altitude buffeting.
You will bleed off your energy rapidly and convert an overspeed right into a high-altitude stall.
It is also vital to distinguish between a nose-high and a nose-low upset recovery because the energy states require different handling.
In a nose-high upset, your priority is lowering the nose to regain airspeed. This may require reducing thrust to eliminate the underwing pitch-up moment.
Or even banking up to 60 degrees to let the lift vector pull the nose toward the horizon naturally.
Conversely, in a nose-low upset, you are in a high-energy dive. The critical and counterintuitive factor here is that the aircraft can still be aerodynamically stalled, even while pointed straight down toward the ground.
Right. If you are stalled in a dive, Pulling back on the stick will only tighten the dive, increase the load factor, and accelerate your descent.
You must push the nose down further to break the angle of attack and resolve the stall. Then roll the wings level in the shortest direction and finally execute a smooth pullout.
You have to manage your thrust and drag carefully to avoid exceeding the positive 2.5 G structural limit during that pullout.
This brings us to the actionable takeaways for you on the line. The cognitive lockup observed in these accident reports can be broken through disciplined procedural adherence.
First, actively vocalize and confirm the current flight control law on the ECAM and PFD during any anomaly. When you state alternate law out loud in the flight deck, you actively prime your mental model for the loss of the digital protections.
Second, anticipate direct law. If you are operating in alternate law and you call for gear extension, you must expect the immediate loss of auto trim.
Prepare yourself to manage the TA just manually the moment the gear drops.
Finally, utilize the pilot monitoring for progressive intervention. If the pilot flying experiences cognitive tunneling and applies inappropriate inputs like holding aft stick during a stall warning, as we saw in the telemetry, the pilot monitoring must aggressively intervene.
Verbally correct the action immediately, and if necessary, press the sidestick takeover push button to assume physical control of the aircraft.
The integrity of the flight relies entirely on the crew's ability to seamlessly transition from system managers back to conventional aviators the moment the digital protections degrade.
Recognizing the actual aerodynamic state is paramount over recovering a specific altitude or managing secondary system alerts on the ECAM.
We will leave you with the final operational consideration as we wrap up this deep dive into the incident reports.
Airbus continues to deploy fly-by-wire software updates like the pitch attitude limitation and alternate law, and adjusting flight warning computer priorities. These are specifically designed to prevent the exact accident chains we analyzed today.
And these digital safety nets are undeniably effective at keeping the aircraft flying. But as the software becomes more robust and alternate law stalls become virtually impossible without multiple cascading system failures, consider this.
Are we inadvertently pushing the boundary of automation surprise further down the line?
Exactly. By engineering out the aerodynamic edge cases, we make the eventual manual recovery even more alien and startling to the next generation of pilots who will face the moment the logic finally fails.
Keep that in mind on your next rotation.